Thanks for coming out again, guys. And apologies to anyone who's seen this talk before. So I gave this one a bunch of times because after I finished my PhD, I worked in industry for a bit, so I had no new science that I was allowed to share. So if you've seen it before, I'm sorry, but you're going to see it again. So that's it. Well, you came out here. I didn't make you come here. So if you've seen it before, it's your fault. There's a few repeated slides. So I went through this one yesterday, but I'll go through it again. So we're talking about orogenic gold. So gold related to orogeny, which is the worst term ever. But these things are metamorphically sourced, depending on who you ask, or deposits. Look like quartz vein hosted sort of gold deposits, right? So for the source, we usually say metamorphic fluids, low salinity, water rich, CO2 rich. You have devolatilization of a metamorphic source rock around amphibolite conditions. So it's normally pyrite to peritite for metals and sulfur. And then water comes from dehydrating hydrous minerals. Mesothermal depths, mid-crustal block. Temperatures there are they can be lower than 300 degrees when they come from. Not too much higher. You can't get too much higher for orogenic deposits there. Transported as sulfur complexes, so gold disulfide or gold thiosulfide complexes at near neutral pHs. And they're usually found in higher order structures, fold hinges and stuff like that. So not often in regional faults. I've only seen one orogenic gold deposit on a first order structure, and it wasn't very big. Not to say they don't exist, they're just not as common. For mechanisms on how you make gold come out of a fluid, so wall rock sulfidation, reacting with reduced carbon, you could have phase separation or a rapid pressure decrease. And these things are normally hosting greenstones in the Archean and slate belts in the Phanerozoic for the younger deposits. So this is the little life cycle of these things, as I like to say. Oh man, how many people hate more Coulomb diagrams? Don't put your hand up. We all love these things. So when we're talking about these deposits, you usually have the gold source from the metamorphic fluid production is quite deep. So maybe 18 kilometer steps, amphibolite facies, that transition. That's when you have the breakdown of pyrite to peritite. And then you have a stress transfer. So you have an earthquake, and the fluid can be flushed up large structures and into sort of higher order structures. The reason I have the more Coulomb diagram there is because we're going to talk about not really the earthquake stuff. This is almost the antithesis of the talk I gave yesterday. So yesterday I wanted to talk about what happened during earthquakes and quartz rattling and piezoelectricity. I'm mainly going to talk in this thing about interseismic periods. So periods after the earthquakes or in between earthquakes when we make these things. And how these things work is that because the reverse faults that we find orogenic deposits on are usually quite steep, 70, 80 degrees, you need something that helps them fail. So most thrust faults, sort of a textbook thrust fault wants to be like 35 degrees. That's as steep as you like to get them. But these things are, inverted normal faults that can be 80 degrees. So how do you make that fail? A great way to make that fail is to increase the fluid pressure that's on these things. And that fluid pressure comes from the metamorphic fluid that we're generating deposits from. So in order to make a fault fail, just very simply, you want to hit that thing called the failure envelope. So this guy here. And the two ways you can do that is increase differential stress and make this circle really big so you intersect it. Or if you put in poor fluid pressure, you can just drive that circle this way. And then you can have that, your rocks can fail. So poor fluid pressure is quite important when we talk about these deposits. And if you want to look at sort of the earthquake cycle of these things, we basically have a differential stress buildup and a fluid pressure buildup. As the thing seals, you can have an earthquake, which opens everything up. So differential stress drops, poor fluid pressure also drops, and then it builds up again. And this period in between is called the interseismic period, or I call it interseismic period. And that's what I'm mainly going to be talking about for this talk. So again, I showed you this thing yesterday, multiple earthquake events, multiple fluid events, and gold related to those things. So this is what I call the nugget problem. It's not like the trying to drill or do a resource model nugget problem. It's more the thing that I like working on, and also Evan likes working on, and many others. It's making really, really large gold accumulations out of fluids that don't necessarily should be able to make them. So that's a sample from the Fosterville deposit where I did my PhD. That thing was about 30,000 grams per ton. And then they get more and more impressive. And then there's stuff like this that exists in nature, the old welcome stranger. I'm not going to say that came directly from orogenic gold deposit, because when you get gold nuggets, you get superficial processes and lots of things can help contribute to their growth. But the point is gold gets really, really big. And surprisingly enough, we're not really sure how or why. But that's good because it means we have a job and we can keep studying these things. So the place where I did my PhD is the Fosterville gold mine. So I have that here. So this is a map of central Victoria. So in Australia, I live in Melbourne, I live here, and this is the Central Victorian Gold Belt. This is the geology. It's actually pretty simple geology, which is good for when you're trying to figure out a complicated problem. So for the most part, we just have Cambrian and Ordovician turbidites that overlay a basaltic basement, and it's standard fold thrust geometries. The cross section here, the regional cross section, we have Fosterville there, and other famous things like Bendigo and Sol are also existing in that field. And this is what the Fosterville mine looks like in cross section, or at least that's what it looked like in 2018 in cross section. And the samples that I was really interested in studying, are these ones. So for Fosterville, they have this zone you might have heard of called the Phoenix zone, which is where they're pulling a lot of good stuff. Or the Swan lode is something you might have heard if you're up to date on those things, and that's where they get the really fantastic visible gold. So what I wanted to study is how do you make these really fantastic visible gold samples, and they were nice enough to give me some. And these are the samples that I was given. So I was given these things. I knew very, very little about structural geology, but one thing I noticed was that there's these black squiggly things that are often associated with the gold. And I was like, hey, man, what are these things? I have no idea what's going on. So I did some, this is neutron tomography. So we can basically just do 3D mapping of minerals. And one thing that I think you guys can see is that the gold is often in these like planes, and those planes are where those stylitic seams are, these pressure dissolution seams are, whatever term you like to use. And I got very, very obsessive with why that was the case. And that's a very accurate representation of me in my PhD. You can talk to Andy Tompkins about that if you like. I was a bit of a crazy person. So I was like, all right, what are these things? And why is gold always associated with these things? So they're pressure dissolution seams. So it's just how you make these. It's dissolution of minerals under non-hydrostatic stress or non-equilibrium stress. And it will reduce the rock volume. So some minerals will pressure dissolve. So if you squish them, they'll turn into a liquid and they can migrate. And they can migrate anywhere from microns to even kilometers in some case away from wherever they're being dissolved. And the stylitic seam itself is defined by basically elements that won't dissolve under pressure. So they're the dirty things left behind. So the anatomy of these things looks kind of like this. So you have the actual stylitic seam or the pressure dissolution seam here. They often have these sigma 1 parallel tension fractures. And then the seam itself will be made out of insoluble stuff. So at the grain boundary, it looks more like this. So a dissolution out of contact, and then you can diffuse these elements out of that contact until they basically stop moving wherever they like. So whether they fill in nearby pore space or if they migrate very large distances, it depends on the sample that you look at. So if you look at it sort of on a tectonic block model, this is what it would be for a compressive regime. So you have principal shortening axis horizontal here. Tension fractures will be given subhorizontally, and then vertical stylites, assuming that there's nothing that would play with that geometry. So there's a guy named Ren Green who he's shown that you don't need pressure to do pressure dissolution. So there you go. That's something crazy. So he was making stylites with about, I think, 6 atmospheres of pressure, which is not a heap. I mean, I probably weigh more than 6 atmospheres of pressure, I think. And what he sort of showed it up to was that it was actually it was an overlap of these things called electron double layers, which every material has. It's basically a surface potential. It's a surface energy. And the way that he envisioned this is that if you brought 2 dissimilar minerals together, where one has, let's say, a positive surface charge and one has a negative surface charge, if you link them together and there's a fluid medium between them, you basically make a battery. So anyone who asked me, hey, how'd you get into piezoelectricity yesterday? It's Ren Green's fault, really, because I was studying stuff like this and then got all into surface potentials and things like that. So this was from his paper here, this little thing on the left. And he had quartz and mica, and he was making stylites, and he brought it up to this metastable reaction here, where he had a dissolution of quartz by some calcium and some hydrogen that was in a fluid phase interstitial between the minerals. And it caused this sort of cannibalism of the quartz to make this metastable thing. And then you make a silica hydroxyl out of that. The thing about that is it has an electric field. So it is going from mica, which will be the opposite charge of quartz. So you end up making basically just a liquid battery between these 2 surfaces. And I thought that was really interesting because when I was looking at Fosterville or lots of other orogenic gold deposits, there's often a lot of wall rock selvages in them that fall out during the earthquake action. And those wall rock selvages, at least in the Phanerozoic dominantly, are bits of shale that come out. You have that competency contrast and they can fall in. And these shales are made out of mostly micaceous minerals. So when I seen Wren's results, I immediately was thinking about, hey, what's this going to do if you have an orogenic quartz vein? And then all these pink arrows that are on the wall photo there is where there's visible gold in that stope. So the story started off fairly simple. It was something like this, where if you had a gold-bearing quartz carbonate vein that has a little bit of gold in it, it may be economic. It might not be economic. But over time in these interseismic periods where the whole system's under shortening, but it's not failing, you should have pressure dissolution of the vein material. And then you could sort of release this gold as an insoluble element and it'll stick to the stylitic seams. It'll stick to these positive sort of micaceous or shale seams. So you almost have a residual gold increase during the interseismic periods of ore deposit development. And then when I was having a closer look, doing some CL, is Bruno here? Yes. Yeah, hey. Was it you who was asking me about quartz textures yesterday? Or was it someone else? Anyways, that's the messy quartz textures I was trying to describe yesterday. When I was having a closer look at these things, I was finding sort of these little tiny particles here. I could just say they're sub-micron, but I started thinking about nanoparticles and what that could mean. And then, yeah, here we go. I did some work with Danny Furgerup, and we found a couple. So this is how I got sort of the nanoparticle stuff, which was quite exciting. But so a nanoparticle, for those who don't really study them, like it's just got to be a nanometer in at least one dimension. When you put them into a fluid, they're sometimes called colloids or they're colloidal gold. But they do really weird stuff because they're large surface area to volume ratios. So they have really strange potential energies on them or superficial energies on them, sorry. So they behave really differently to bulk equivalent solid materials. They normally form from supersaturated solutions. So you just need to have a boatload of gold into a fluid that just can't really hold it. Which means they form in really far from equilibrium conditions. So if you had some bulk fluid with some concentration of gold that's happy, let's say it's a ligand bound, whatever, if you can remove a lot of that fluid or if you can make that fluid very unstable chemically, you can make nanoparticles that way. But they're often very transitory. They don't exist for long because they want to reduce their energy as quickly as they can. The reason why this was exciting was that a 4 nanometer gold particle has about 2,000 gold atoms in it, which means when you're trying to explain how you make a large gold nugget in a vein, you don't need to have all that fluid there in the vein to explain how much gold you have there. There's a little bit of a caveat to that because you're going to have to start with some fluid to start. So, it's just that you don't need the recorded evidence of that much fluid being at the site of the gold nugget in order to explain it if you start doing nanoparticle stuff. You still have to deal with trying to generate them and, how far do they come from, etc. But you can at least start trying to explain these really crazy gold nuggets or gold accumulations that we see in quartz veins. So this is the sort of the life cycle of these things. So you can have gold start as ionically bound gold, or maybe it started as a colloid if that's the story that you like. That's entirely up to you. And then you need to have supersaturation. So you need to have rapid saturation of gold in the fluid, and then you need to overcome its aggregation barrier to stick gold nanoparticles together. These things can repel each other if they're similarly charged. So you'll need to have some process that will make them stick. And there's many processes that can do this. So there's diffusion limited aggregation. So you could do it over some sort of potential, whether it be electrical, chemical, thermal. You can have orthokinetic aggregation, which is physically smacking them together. Processes like Ostwald ripening, where nanoparticles will coalesce to reduce their free surface energy and cannibalize each other to make bigger particles. And then oftentimes their sort of nanostructure is destroyed as the nugget recrystallizes, especially where gold is quite malleable. It's hard to always have evidence for these things having existed. So I put all that together for this sort of aseismic of orogenic gold thing, or sizes and everything in this case. These guys are great. These are sort of gold only stylites. So I found in Fosterville. It looks like somebody just marked with a crayon on the rock face. But if you look at these under thin section, it's just a dissolution seam of gold in quartz. It's the only other phase that's in it. So in the story that I told, the first step is that we have to generate nanoparticles. We need to put them into the vein system in order to begin with. That would be this part. So having a fluid, so a metamorphic fluid that comes up during earthquake times, goes into the vein surface or fault surface, and then it needs to supersaturate. My favorite example for how to do this in a Phanerozoic or like a slate-hosted deposit would be a mixing of a bit of methane. So there's a paper by Nathan Shepard, I think, in 1989, where they mixed 4 mole% methane with a typical H2S bearing orogenic fluid. It caused phase separation, and all the H2S jumped into the vapor phase. So I think that would be my favorite excuse as to how you could supersaturate the fluid phase for a Phanerozoic orogenic gold deposit. And then because we're dealing with an earthquake system where things are quite aggressive and rattly, I'd like to stick these things together with orthokinetic aggregation if I had to blame one of these things. And then at that point, you'd have coalescence of the metal precursor or little nanoparticles into slightly larger particles. So things on, let's say 10 nanometers and bigger. And so things that would look like this. So you'd have a quartz crystal or a quartz vein that has little bits of gold sprinkled in it. Like I said, it might not be economic, it might not even catch your eye at all, but those things are living inside of the quartz crystals and quartz vein. So then after that, we need to aggregate them, or we need to start making the observations that we actually see in the rock. So how do we do that? And that's when I start bringing in red green stuff. So in this sample here, we have stylitic seams here that are kind of coated or dusted in gold. I really like this photo. So this is taken sort of on the other underside of a lamination. So this thing here is mostly graphitic shale. And then it looks like someone sort of painted it or dusted it with gold on one side so that the rock was cracked directly on a stylitic seam in that case. And you can see the gold dusting on the back. And then a thin section showing something similar. We have a bit of arsenopyrite from all rock mineralization and gold along the seam. But in this case, I reckon you would have the negatively charged nanoparticles, as they'd like to be, sticking to the positively charged micaceous surface or shale surface. So as you pressure dissolve the quartz grains, the little bits of gold nanoparticles are liberated, and then they'll stick to basically the oppositely charged surface, which in our case would be the stylite or the shale. And then that will be an example of diffusion limited aggregation. So this is the aggregation under the diffusion towards an opposing electrical charge. So it's just magnets really in this case. And then one of the last settings that we had was these gold that's on little tension fractures perpendicular to stylitic seams. So stylites here, we have these perpendicular tension fractures, and you can see gold at the sort of terminations of these things and along those things. And in this case, I think it's actually a bit simple. I think it's just that's where you have your volume generated. So you have a pressure differential as you open up a tiny tension fracture. Any fluid existing along the stylitic seam will rush in to fill that fracture just because it's where there's free space, right? We don't like having free space underground, and we can make those kinds of textures there. And oh yeah, I was getting asked this question a lot. So there's a lot of assumptions on this. So I'll be upfront with them, but I kept being asked like, how much enrichment do you think happened? Or basically how much pressure dissolution do you think has happened? So in the case of this sample here, I took a volume of around this stylitic seam here that was rich in gold. And I took the same amount of volume, but I took it away from the stylite seam in the center of the vein. So the assumption here is that the vein would have been homogeneously mineralized throughout before pressure dissolution happened. And I ended up with having a 72% relative enrichment of gold, or if you like it, 72% dissolution of quartz. So that's just the math I did there to do it. But yeah, we worked with the assumption that the vein was homogeneously gold mineralized in this case, and then we just removed enough to explain that stylite. And one of the very last settings I looked at was the sulfide hosted gold. So pyrite and arsenopyrite hosted mineralization at the Fosterville deposit. So in this case, this looks like it's 2 samples, but it's 1, and I rotated it so you can see where I sampled it. But I just took a Dremel, and I have a piece of wall rock in the vein there that becomes progressively more pressure dissolved. So the B point here is sort of the least deformed wall rock. C is the next one, and then D and E. It becomes more and more pressure dissolved or more strained. And I looked at how the gold setting changed within this. So for this arsenopyrite, we have gold that is parallel to the crystal zoning, the crystal structure. So I believe that would be AU plus, or at least sort of lattice parallel, lattice bound gold. And then as we get more and more deformed, you can see the setting sort of change. This gold here is on kind of longer fracture. This one here is actually a pyrite, and you can see the green zoning is the arsenic content, and it's all sort of little nanoparticles on fractures here. And then this thing here is completely, invade, dissolve. It's all porosity on this thing here. That's another arsenopyrite. So this one I was looking at molar model stuff. So the molar model thing talks about the different surface energies and the different type of conductance that sulfides can have. This is actually related to arsenic content when it comes to pyrite or arsenopyrite. So if you have increasing arsenic content, you could actually change the kind of conductance a pyrite has from an N type, which a negative type conductor, let's say, to a P type, positive type conductor. And when these things are touching each other, you actually have the donation of electrons across one towards the other. So the one that's anodic will actually donate towards the cathodic one. So an N-type conductor will shoot an electron at a P-type conductor if they're touching. And the reason that this becomes kind of interesting is that if there's gold that's either as a nanoparticle or even as a ligand-bound fluid phase, if they go across an NP junction, the gold can become reduced. They can get hit by an electron, fall out of solution phase. This effect can be extended if you have a conductive surface around. So if we have a graphitic stylitic seam, you could actually have that go further than being directly juxtaposed upon one another. It could actually go a little bit further. How far? I'm not positive. But nanoparticulate gold likes to go to P-type affinity. So again, they stick to the opposite charge. And then along the NP junction, so I have them highlighted here, you can see that we have fractures in gold accumulated next to these things. So it's sort of particles of gold where you have the green arsenic zoning in pyrite there. And then for arsenopyrite, it's just having more arsenic content. So, just these highlighted bits of green again. So along those junctions is where we could see that there was a lot more gold being deposited. So how I like to relate this part is where you have shortening in your vein surface. You can have this sort of cataclysm and crunching up of the sulfides. And when you do that, you can open up fractures and open up porosity that makes it available for fluids to percolate by, and you can do these NP junction reduction type things. So we put it all together, you get this sort of entire model. So you start off with a sealed vein surface. You have an influx of metamorphic fluids. It helps it fail. The entire system can break open. That's where you can have gold actually come into the system and be introduced. You can make little tiny nanoparticles, lock them up into a quartz vein or into a quartz crystal. And then when the whole thing goes under net shortening again, but isn't failing, is when you have pressure dissolution, sort of cataclysm and crunching up of any sulfides that are in wall rock selvages within your vein surface. And these living in this differential stress diagram, we have A, B, and C related to the top here. So this is where things are sealed, differential pressure is increasing, fluid pressure increases. B is when things open, so you actually have your earthquake action. And then C is the interseismic period where things shorten, but they're not failing and fluid pressures are building up once again. So the key points of this thing is, I think we all knew this, but this thing's 6 years old now. Traditional fluid chemistry is it's difficult to explain the really, really high grade gold mineralization you get sometimes. And I tried to explain at least these fossil samples by using pressure dissolution creep and gold nanoparticle theories. And then there's some stuff I had for fossil, so looking at sort of the angular relationship between the paleo stress axes as well as the vein orientations for how much pressure dissolution you can get. And then you have basically a refinement of gold along these stylitic seams, and it's accelerated by wall rock selvage content. So if you have many, many wall rock selvages or many, many laminations in a quartz vein, you basically have more pressure dissolution fronts, so you could remove more not ore from your ore vein. And then it just puts an emphasis on the aseismic period of orogenic deposits, because we all focus on the exciting earthquake part, but not so much in the in-betweens. And it also provided a little bit of a link between sort of vein-hosted native gold and then refractory gold, and having them coupled together a little bit in their evolution. So crunching up refractory gold ores and releasing that as nanoparticles and letting them percolate through vein surfaces and maybe build something a little bit more visible or a little bit more macro. So not having them as two separate pots, but trying to make them talk to each other. And that's that's it. And it was published whenever 2020 or 2019 or something. And if you guys want either of these papers, this one or the piezoelectric one, you can shoot me an email. I'll send it to you, or I think Steph has them as well. And yeah, thanks. If you have any questions, go ahead.